Hi, this is Professor Lee lecturing on Introduction to NMR. For about next 10 minutes, I'll be answering questions such as, what is NMR? Why do we need to learn it? What information does NMR give? Something to note is that the initial video was recorded when NMR was introduced in Chem 225 or Orgo 2. A couple years ago, Dr. Gurney and I decided to teach NMR in Organic Chemistry 1 because of the importance of research integrated labs. You'll know that in the lab, you'll be using proton and carbon NMR extensively to find out the purity or the identity of the compounds. So please ignore any references to Chem 225 in notes or in video. NMR, IR, mass spec, a lot of these instruments are tools that we use to analyze compounds, and they belong to a subset of organic chemistry called analytical chemistry. And as the name indicates, we analyze compounds to determine, sometimes it's to determine the purity of the compound, and sometimes it's to analyze the structure of the compound. So you've already been exposed to a tool last semester in 114 in which you used IR extensively. And just to briefly review, you used IR to look for either the presence or absence, because the information that something is not there is just as important as something is there. So presence or absence of what? Functional groups. So for example, you often were looking for hydroxy stretch, which could be part of, it could be an alcohol functional group, or it could be water that's present in your sample, or it could be carboxylic acid, especially if it's present with a carbonyl stretch. But you know that carbonyl could be part of an aldehyde or ketone or ester, amides, anhydrides, all these functional groups that you're going to study this semester. You also could figure out if an alkene or an alkyne were present, as well as amines, and there are other functional groups you could look for, but these are the main ones that you look for last semester, right? Now IR is a great piece of information, but how do you determine the exact structure of a compound once you know the functional group? So for example, let's say I have two little containers filled with clear liquid, and I will tell you that one of the liquid is ethanol and the other liquid is methanol. Now, since both methanol and ethanol have OH functional groups, so let me write it out, an ethanol and methanol, and I don't know which is which because they're both clear liquids. All right, so I will take an IR spectra, and in this IR spectra, am I going to be able to tell whether this container is ethanol or methanol? Let's see. So I have here IR spectra of two compounds, and notice that the OH stretch here, which is present in both liquids, and then the rest are different peaks, and you could tell that they are different compounds because the IR is different, especially in the fingerprint region. But unless you had an IR of methanol and compare it directly right next to each other, you're not going to be able to tell just looking at the IR spectrum that, oh, of course, this is from ethanol and this is from ethanol. We don't have a way to do that. So IR is useful in determining what functional group is present or what functional group is not present. But other than that, it does not allow you to analyze the structure of a compound. So this is where NMR is useful. And the purpose of NMR is to determine the map of carbon-hydrogen framework. Or another way to say this is to determine exact structure. Alright, so I'm going to show you NMR spectra of these two liquids that you saw. Alright, so I've taken an NMR of this one and NMR of this one, and I already showed you the IR, and these are the NMR spectrum. Now, what you're looking at is not a carbon spectrum, but a proton spectrum. So you already took some carbon NMRs last semester, and this semester we're going to be focusing on proton NMR. So here's one proton NMR spectrum, and here's the other. Notice that they're drastically different. And because NMR allows you to take a spectra and be able to interpret the carbon-hydrogen framework, and because I know how to do that, I know that this spectra comes from ethanol, and this more simpler one is the spectrum of methanol. All right. Now, so the NMR, the instrument, when we were operating for the proton NMR, somehow the NMR, quote unquote, I'm going to say, sees the protons and record these protons as peaks in a spectra. So how does NMR see protons and record them as peaks? All right, that how is going to be addressed in the next lecture. But right now, what I want to briefly give you an overview is the information that NMR gives. There are three information that NMR gives, and that is the type of proton that's present. All right. So, for example, is the proton that you're looking at, is it from an aliphatic or aromatic, or is it an alkene proton or an alkyne proton? So we could determine this by looking at the proton NMR spectra, and depending on where it shows up on this x-axis, we could type them in general. You know, if something shows up in this region, we know what type that is. If it shows up in this region, we know what type it is. This is where the aliphatic shows up. This is where aromatic shows up, for example. So by knowing where things show up, you know what type of protons present, right? The second information that NMR provide is the ratio of each type of proton. And we call this integration. And all this is basically looking at the, so like in this NMR spectra of ethanol, this is one type, this is another type, and this is another type. So I have three types of protons, and then the area underneath which is called integration, represents the ratio between this type, and this type. So we'll be looking at the area of this and compare that to area of this and compare that to area of that. And that's what we are going to be able to figure out, that I only have 1 of OH and 2 of the CH2s and then 3 of the CH3 protons. All right. And then the third information that it gives is a neighboring info. Okay, and that is determined by the splitting pattern. So, notice in methanol, the peaks are both what we call singlets. All right, they're not complicated, they're just one peak. But in ethanol, notice that this peak, we call that a quartet because it's really 4 peaks that are making up of one type of proton. And here's a singlet and here's a triplet. So that information, all right, the singlet, the doublet, the triplet, and the quartet, tells you something about not the proton that you're looking at, but the neighboring proton. So that's how we could figure out the carbon-hydrogen framework by knowing these 3 information. So the goal of this unit 1, is for you to be able to draw a proton NMR given structural formula. All right, and after you're able to do that, I expect you to be able to, given spectra, propose structure that is appropriate. Okay, that means that if I gave you this structure, this structural formula, I expect you to be able to draw this. All right. Now, if I gave you this spectrum and didn't tell you what the structural formula was, then by analyzing this NMR spectrum, I expect you to be able to come up with a structural formula that corresponds with the spectrum. Okay, so that's your goal by end of this unit. And so this concludes the NMR lecture 1, the introduction, and the next one will